Blender 5.0 is now out, and it brings some massive upgrades. Better compositing, repeat zones for shader nodes, brand new modifiers, and a lot more. But for me, the geometry nodes are of course what I'm most interested in, and there's a use of the new nodes I haven't seen anyone else talking about. In this file, I have a particle simulation that's bouncing off a bunch of objects, and using the old method, Blender has to sample the geometry of the colliders every frame to find the closest position. This works, but can be really slow depending on what the collider geometry looks like. You can see my viewport is chugging. But if I switch over to this new method, we're now running it in real time. Same amount of points, same colliders, but 10 times faster. How's this possible? It all comes down to a concept called a lookup table, or LUT. If you've ever color graded footage in something like DaVinci Resolve, you've probably heard of LUTs before, as they're commonly used for color grading presets, but that's far from their only use. Most LUTs you'll encounter are stored as .cube files. You can see this in DaVinci for yourself. They store data as an RGB color cube, a 3D grid where each point corresponds to an input color and defines what that color should be converted to. You can imagine that as I increase the density of points here, we have all possible RGB values in this cube. Currently, this RGB cube is just the default one, but I can adjust this however I want. Maybe make it tinted towards an orange/blue palette. Then, say I save this as a LUT, the software can use this cube file as a lookup system. It takes the original RGB value, checks where it sits in the cube, and outputs the corresponding transformed color. This is an easy way to store color grading presets, but it has another benefit. It's incredibly fast. Since all of the data is pre-computed into a grid, the only calculation that's needed is a simple lookup. In Blender, the new grids can be our table, and the lookup is a simple grid node. This node is a lightning fast if the grid is baked. Now, we're going to dive a bit deeper into how this animation was made with this technique. This is a simplified version of the file for that vine animation, and it uses grids for all of the interactions with objects. If you would like the full version of this file, along with all the other Blend files I use in the production of my videos, you can join my new Patreon. That's right, I made a Patreon, and it's where all of my future Blend files will be. You'll also be getting work in progress updates from me on upcoming videos there, and early access to them. These videos take a lot of work to produce, and I have some bigger ones coming up, so any extra support is greatly appreciated, and Patreon is now the best way for you to do that. I've tried to make it worth your while, but of course, no pressure. Now, back to the grids. So I'm just going to go through every single node in this file. If you would like to skip to the grid stuff, that would be this. You can skip to it in the timestamps. First off, before we do any simulating, we have our emitter, and in this group, we take our emitter plane geometry and distribute random points on it, or I have an option to just have a bunch of points in the middle of the plane, and this switches between them. And then we store their index so we can use it later to turn them into curves. We then pipe this into the second input on the simulation zone. The first input is used over here to keep track of all of the points with this join geometry and the all points output. But for now that we have points in our simulation zone, we first update them in this node group where we just offset their position by the velocity. Then we add an attraction force to this target empty via these nodes. We first get the position of the target empty and then subtract that from the position of our points. We then normalize this, and this will give us a vector towards the target empty. Then just adjust the strength with the scale node and add it to the velocity. Then adding a noise force, very similar. Here we get a noise that evolves over time, and it's unique to each point using this index into a hash value node. We add that to the W. Here we take the color of this noise texture and put it into another scale node to adjust the strength, and then add it to the velocity like before. Now, we get onto the grids, and these are the objects we'll be using for collisions. You can see here I have two nodes, grid LUTs, which we went over what a LUT is, and object forces and collisions. First, I'll show you what is inside of the grid LUTs node. In here, we have a bake node, which is getting all of these inputs: the sign distance, the mesh position, the mesh normal, and the STF mesh. The mesh is really just for preview purposes. Going back to the start of this node group, the first thing we do is just get our colliders, and then we get the collection info, realize them so we can actually do things with them, and then turn them into an STF. This voxel size slider will determine the quality. For this scene, 0.5 seemed to work, but I probably could have gone with a higher number and therefore lower quality if the bake times became an issue. We then do two things with this. On the top, we just feed it directly to the bake node, and on the bottom, we bring this over here and turn it into a mesh. This mesh is then used to sample the nearest position and normal for later use in the simulation. But these are fields, not grids. We can use the field to grid node, but if we just used our SDF as the topology, it wouldn't work. This topology input is kind of specific. This is easier demonstrated if I distribute a bunch of points in the sign distance field. You can see when I distribute them, they're just all around the objects, nowhere else. But what we want is a constant density across the entire area where we're simulating. For this, we go back here and we make a bounds cube. We get this bounds cube with an object info node, and then we sample the top point and the bottom point, which we feed into a volume cube min and max. You could automatically determine the volume cube bounds, but for me, this was the better solution. We then get the density of this volume cube with a get named grid node. You can see that this is a constant density grid. But if we just plug this straight in, we would not get what we want. You can see that if we do that, everything is kind of grouped into large squares. And the reason for that is because this is a sparse grid. What that means is because this density is constant, Blender doesn't bother calculating every voxel to save performance. But we actually want every voxel to be active, so we use a voxelized grid node, and that solves our problem. Then back to the field to grid node, we now have these grids as we wanted them. We can then bake this, and then sampling it is basically free, like I said in the intro. So let's do that now. You can see all 3 of these grids are piped into this group, which we will go into now. And here I am sampling all of them. So here we sample the sign distance, the position, and the normal. And then we have 2 more groups, one of them for object collisions, and then we add a random tangent force. The object collisions just require the sign distance and position, and we'll get into that first. In this node group, we start by capturing the position and selection. So we use the capture attribute with the position node, and here we get our selection. We can test if one of our points is inside of a mesh by just testing if the sign distance is less than or equal to 0. This is because any point that is inside of a mesh will have a negative value when we're talking about sign distance fields. We then move on here, and we set the position of our selection to the mesh position. We then use this old captured position to calculate a new velocity by subtracting it from our current position, normalizing it, and then scaling it by the length of our old velocity. And we update that here just on our selection. Then we move on to adding a random tangent force, which we just need the mesh position and mesh normal for. This one is a little more complicated in the vector math, but I won't dive too deep into it. Here, what we're doing is we're basically getting a random vector that isn't pointing in the same direction as our mesh normal, which we then take the cross product of with the mesh normal and normalize it. This will give us a random tangent force. And if you don't know what a tangent vector is when we're talking about meshes, it's basically just a vector that is perpendicular to the normal. And in this case, we're getting a completely random one. Up here, we get the unsigned distance by taking the distance between the nearest mesh position and the current position of the point. We then remap that distance with a map range and scale this random tangent vector by that distance so that it only applies when the points are close to a mesh. We then adjust the strength like we did before with a scale node, and then add that to the velocity. And that's it for the grids. After we do all of that, we go in here to this reset speed node where we're just resetting the velocity length to 0.1 so that they stay at a constant speed over the entire animation. Then this gets fed into the join geometry where we can get all of our points together, which can then be turned into a curve and then turned into vines, which I won't go over the process for turning them into vines here, but that is on my Patreon if you want. Hopefully that node walkthrough helped highlight how useful this new greedy system can be. But if you take nothing else away from this video, I hope it's that optimizations in geometry nodes and other areas can come in ways you'd never expect. Volumes in geonodes have always been a pain point in terms of performance. I used to avoid them all the time. But lo and behold, Blender releases this new volume grid system and it can be used to optimize tons of different kinds of simulations, simply by thinking of techniques used in other areas of CG, in this case color grading. Knowing these little things about areas outside of our expertise can really help us become more rounded artists. But speaking of optimization, I recently updated one of my add-ons to be way more optimized for making anime smears in Blender. Go check out this video next to learn more about it.